All right, to start getting ready 35 here, we're going to be given some systems of inequalities and then some possible solutions. And what we're to do is check each of those possible solutions to see if it does work for the system. Now remember, to be a solution of a system, whether it's equations or inequalities, it must work in both or in all of them, however many equations or inequalities you have. So in number one, choice A is the point 6, 10. So I need to substitute those values into both inequalities to see if they work. All right, so for part A, I'm going to substitute, well, let's write down the inequalities first. 3x minus 5 and y is greater than or equal to x plus 2. And then I will substitute 6 for x and 10 for y into each of those. So 10 is less than or equal to 3 times 6 minus 5. Well, when I try to simplify each side, the 10 can stay as is. 3 times 6 is 18, minus 5 is 13. So I end up with 10 is less than or equal to 13, and that's true. In the second inequality, I replace the y with 10, greater than or equal to the x is 6. So 10 is greater than or equal to 6 plus 2 is 8. That is also true. So since both inequalities are true, that means A is a possible solution. That does not mean we're done, right? There are infinitely many solutions to this system, so we still have to try B and C also. So in B, if the y value is 4, less than or equal to 3 times our x value 1 minus 5. So 4 is less than or equal to 3 times 1 is 3 minus 5 is negative 2. So 4 is less than or equal to negative 2. That's false. So I don't even have to check the second inequality. I know if it doesn't work in this first one, it's not a solution to the system. Okay. And then part C, 8, 15. So I replace y with a 15, replace x with an 8. So 3 times 8 is 24, minus 5 is 19. So 15 is less than or equal to 19. That's true. So I do need to check the other one. So again, the y value is 15. That would be 15 greater than or equal to x is 8 plus 2. So 15 is greater than or equal to 8 plus 2 is 10. That one's also true. So since it worked in both inequalities, C is also a solution to this system. Same directions for number 2. Okay. So rewrite my inequalities up here so I can work below them. So in choice A, I replace y with negative 5. That's greater than negative 2 times the x value is negative 2 plus 9. Well, negative 2 times negative 2 is 4 plus 9 is 13. Negative 5 greater than 13, that's already false. So we're done with A. It can't work. B, negative 1, 12. So replace the y with the 12, greater than negative 2 times negative 1 plus 9. So 12 is greater than negative 2 times negative 1 is 2 plus 9 makes 11. Well, that one's true. 12 is greater than 11. So I try the other inequality for B. So 12 greater than or equal to 5 times negative 1 minus 6. That's 12 greater than or equal to 5 times negative 1 is negative 5, minus 6 is negative 11. That one's also true. 12 is greater than or equal to negative 11. So B worked for us. It's a solution. And the last one, C. We replace y with a 0, replace x with 5. So 0 is greater than negative 2 times 5 is negative 10 plus 9. Negative 10 plus 9 is negative 1. So 0 greater than negative 1, that is true. Try it in our second inequality. Place y with 0 greater than or equal to 5 times the x value of 5 minus 6. So 0 is greater than or equal to 25 minus 6. 25 minus 6 is 19. So 0 greater than or equal to 19 is false. So this one does not work. One more like that. Number 3, again, we'll write our original inequalities up here and just work down from each one. So, selection A, I replace y with negative 5 less than negative a half times negative 2 plus 9. Negative 5 is less than, now negative 2 times, negative a half times negative 2 is 1 plus 9, which is negative 5 less than 10. That's true. So we have to go ahead and try the second inequality. Replace y with negative 5 greater than 6 times negative 2 minus 10. So negative 5 is greater than 6 times negative 2 is negative 12 minus 10. So negative 5 is greater than negative 22, also true. So A, the point negative 2, negative 5 is a solution. B, 7, 3. So replace y with 3 is less than negative 1/2 times 7 plus 9. 3 is less than negative 1/2 times 7 is negative 3.5, so negative 3.5 plus 9. 3 is less than negative 3.5 plus 9 is 5.5. Yes, 3 is less than 5.5, so that's true. Second inequality, replace the y with 3 greater than 6 times x value of 7 minus 10. So 3 is greater than 42 minus 10. 42 minus 10 is 32. 3 is greater than 32. Nope, that's false. So 7, 3 is not a solution to the system. And third one, negative 8, 10. So replace y with 10. Replace the x with negative 8. So I end up 10 less than negative a half times negative 8 is positive 4 plus 9. And 4 plus 9 is 13. So 10 less than 13 is a true statement. Try the second inequality. Replace y with 10. Replace x with negative 8. So let's simplify the right-hand side. 6 times negative 8 is negative 48 minus 10. So 10 is greater than negative 58, which is also true. So choice C, negative 8, 10, is also a solution to our system. All right, directions are changing here. Now we have systems of equations rather than inequalities. And we're really looking at determining the number of solutions. So we're going to decide whether it has the system has no solution at all, which would mean parallel lines. They do not intersect. One solution, which is our normal situation with intersecting lines. And the third and last option is to have infinitely many solutions, which would mean that it's actually two equations representing the exact same line. Okay, so no solution, one solution, or infinitely many. Those are the only options. So the directions tell us that first we are to represent each equation or write each equation in slope-intercept form, and we'll use that to decide which of the situations we are looking at. So the second equation is already in slope-intercept form, so we don't have to do anything with that one. We do need to manipulate the first one, 3x minus 4y equals 13. I'm going to write that in slope-intercept form. I need to isolate the y, move everything away from it. So subtract this 3x, leaving me negative 4y. Remember, the sign in front of the number stays at the number. Can't lose that negative. Is equal to negative 3x plus 13. Lastly, divide every term on both sides by negative 4. So y is equal to, now negative 3 over negative 4 is 3/4 x, and 13 over negative 4 can't be simplified. I like negative 13/4. It would also be okay to call that negative 3 1/4, 3.25. So here's our two equations in slope-intercept form. Now what we have to look at is the slope in each one. So in our first, well, it's actually the second equation, the one that was already in that form, the slope is negative 3. In our orange one here, our slope is 3/4. Since those slopes are different, the lines cannot be parallel and they can't be the exact same line. So these must be, any two equations with different slopes must be intersecting lines. So we have here one solution, and our reason is, the third bullet up there says explain how we came to that conclusion. So we have one solution because the slopes are different. All right. Number 5, same directions. Let's rewrite each of these in slope-intercept form. So first equation, we need to isolate the y. We'll subtract 3x on both sides. So again, we have a negative sign in front of our y term, so don't lose that. Negative 3y equals negative 3x plus 3. Divide everything you see by negative 3. So we have y is equal to x minus 1. If we do the same thing with the second equation, isolate the y variable, we will subtract x on both sides, leaving us negative y equal to negative x plus 1. Now, we weren't solving for negative y, we're solving for y, so we have to eliminate this negative sign in front of there, which actually is representing negative 1. So divide everything you see by negative 1. We have y equals negative 1x divided by negative 1 leaves us positive x minus 1. So we see in slope-intercept form that these two equations are identical. So this would represent only one line on a graph, so there are infinitely many solutions. Meaning everything that works in one equation also works in the other one, because they're actually just the same equation with one of them in disguise. It has infinitely many solutions because both slope and y-intercept are the same. Okay, and number 6. Start with the top equation. Half x minus y equals 30. To isolate the y, we subtract half x on both sides. We're left with negative y equals negative a half x plus 30. Just like we did in the last problem, when we have negative y, we need to divide that negative sign out of there, so divide everything by negative 1. Y is equal to positive 1/2 x minus 30. Okay. Our second equation here, we subtract half x leaving us negative y equal to negative a half x minus 30. And then once again, divide everything by negative 1. So y is equal to positive half x plus 30. So our two slope-intercept form, what we notice is they have the same slope but different y-intercepts. So that means we have the parallel lines on the graph. So this has no solutions because slopes are equal, but the y-intercepts are not. Oh, we have another one. Okay. So starting with 4x minus 2y equals negative 2. Trying to isolate y, subtract 4x, leaving us negative 2y equal to negative 4x minus 2. Divide everything you see by negative 2, leaving us y equals positive 2x plus 1, slope-intercept form. The bottom equation, to isolate y, we'll subtract 3x, leaving 2y equal to negative 3x minus 12. Divide everything we see by 2. Y is equal to negative 3 halves x minus 6. So these two equations, when we rewrite each one in slope-intercept form, they look nothing alike. The slopes are different, and actually that's all we care about. Even if the y-intercepts are the same, that wouldn't change our answer. As soon as you see different slopes, that tells us that we have one solution. These are intersecting lines because slopes are different. Okay, now we're going to graph some inequalities. We're starting here with, in number 8, there's only one inequality. It is not a system of inequalities. So we've, in class, talked about a couple of different ways to arrive at this graph, but I'm going to go ahead and just leave this in, leave it as an inequality and solve for y, as if I'm doing slope-intercept form. So that means I do have to be aware and watch. If I, at any point, multiply or divide by a negative, this inequality symbol has to change. It would go from greater than or equal to less than or equal. So we'll watch and see if we have to do that. First, subtract the 3x out of there, leaving me, again, don't lose the negative sign, negative 4y. As of now, this is still greater than or equal to negative 3x plus 12. To eliminate the negative 4, divide everything by negative 4. So I have y. Now since I divided by a negative, this greater than or equal turns into less than or equal. Negative over negative is positive 3/4 x, and 12 over negative 4 is minus 3. Okay, so I am looking at a slope of 3/4, which we will use that to do our rise over run. And we have a y-intercept of minus 3. So those numbers look pretty small. We'll be able to just use a scale of 1. So begin your graph at the y-intercept, negative 3. And then from that point, we will rise 3 and run 4. That should be enough points to identify the location of our line. So we can go ahead and graph our line from there. Now I do need to take a moment and decide, make sure that I drew the right sort of line, whether it be solid or dotted. Since this is an or equal to, that means the line should be solid. And my last decision is just whether I shade above or below that line. Okay. Well, we can't use the original inequality symbol to make that choice unless we are substituting in a checkpoint. But when we have solved into slope-intercept form, we can trust that sign. So less than or equal tells me to shade everything under that line. So everything under the line is shaded. Okay, and the second bullet up here in the directions tells us, show a point you have tested to prove this is accurate. So that means I'm to select any point out of this shaded region and substitute it back into the original inequality to make sure it does really work. Well, you can choose any point. I would always try to keep it as simple as possible. So if you can pick one of the intercepts, I can't choose 0, 0 in this case because that point should not work. But maybe this one right here, 1, 2, 3, 4, that point is 5, 0. So if I check 5, 0 over here, 3 times 5 minus 4 times 0 greater than or equal to 12. So 3 times 5 is 15 minus 0 greater than or equal to 12, leaving me 15 greater than or equal to 12, which is true. So that means I did shade the correct side of the line. Okay. Number 9, again, just one inequality, not a system. So let's start by solving for y. So I will subtract the x on both sides. I will have negative 1/2 y. I've done nothing to indicate I should change this symbol, so greater than or equal to negative 1x plus 5. Now to get rid of that negative 1/2, what we do is multiply by the reciprocal, which would be negative 2 over 1, or just negative 2. So I need to do that to every term. So I usually just write that like I am writing a distributive property problem. Put parentheses around the entire inequality and distribute the negative 2 to everything. So negative 2 times negative 1/2 is positive y. I am multiplying by a negative, so I need to change my symbol. My greater than or equal becomes less than or equal. Negative 2 times negative 1 is positive 2x, and negative 2 times 5 is negative 10. Okay, again, I think I can fit that on my graph with just a scale of 1. I think there's exactly 10 boxes each way. So my slope here is 2, and my y-intercept, negative 10. So y-intercept, negative 10. And since slope is 2, that means the rise over run would be 2 over 1. So I will rise 2 and run 1. Those points are fairly close together, so I'm going to do that again a couple more times. Rise 2, run 1, until I feel like I can locate the line pretty simply. This is a greater than or equal to, so again, it's a solid line, just like we had last time. And I'm left with just deciding shade above or shade below. Well, since in slope-intercept form, I ended up with less than or equal, I'm going to shade everything under the line again. A checkpoint. Again, choose one that's easy for you to work with. So 1, 2, 3, 4, 5, 6, 7. Let me pick 7, 0. Since that's in the shaded region, when I substitute it in, it should work. So I will substitute 7 for x, 0 for y, and should show that that's greater than or equal to 5. So negative 1/2 times 0 is 0. 7 minus 0, greater than or equal to 5. So 7 is greater than or equal to 5, which is true. So the right thing happened here. It did work just like we expected it to. Number 10, another single inequality. Start by solving for y. So subtract 6x on both sides. I'm left with y is less than negative 6x plus 20. I'm going to have to change my scale this time. My slope is just fine. Rise over run is negative 6 over 1. But my y-intercept of 20 won't fit on this grid as is, counting by ones. So let's say that we're going to use a scale of 2's on the x and y axes. So if my y-intercept is 20 and I'm counting by 2's, that puts that y-intercept right at the very top of the y-axis. Now, my rise over run, if you have changed your scale, as we did here, be very careful with your slope. Down 6, right 1. Going down 6 is really just 3 boxes. Since I'm counting by 2's, that's 2, 4, 6. And to go right 1 is only half of a box. If I do that again, down 1, 2, 3, down or right a half of a box. 1, 2, 3, half a box. 1, 2, 3, half a box. This line should not be solid. This is just a less than sign. So I will need the dashed or dotted line. And I will trust only the inequality symbol when I am in slope-intercept form. It is less than. So I will shade everything under this line. So everything under the line. And this time, we are shading the point 0, 0. The origin is included in our shaded region, so we get to use that nice 0, 0 point to check. Okay, so I'm going to use 0, 0 as my checkpoint. And that is 6 times 0 plus 0 is less than 20. 6 times 0 is 0. And 0 plus 0 is, of course, 0. 0 less than 20 is a true statement. It worked as it should. Another one. 4x plus 4y is less than 2. Solving for y. We need to subtract 4x on both sides. So that's 4y is less than negative 4x plus 2. Divide everything by 4. Y is less than negative 1x plus 1/2, or 0.5. So that y-intercept is 1/2. You could, if you wanted to, change your scale again to count by 1/2. I'm not going to do that. I feel like I'd end up making more mistakes with that scale than just trying to estimate in the middle of the box. So if my y-intercept is 1/2, I'm going to the middle of the first box there on the y-axis. My slope of negative 1 means I'm going down 1 full box. So now I'm in the middle, I'm 1/2 below the x-axis, and right 1. And then I'll go down another whole box and right 1 whole box, and down a whole box and right a whole box. Again, we have just a less than symbol here, so we need a dashed or a dotted line. Let's see if I can extend that. There we go. And our shading, again, we only trust this one, is less than, so we will shade, again, under the line. I can use that point 0, 0 again if I choose to. It is just barely in the shaded region, but it is in there. So I do like to use that one. I'm going to use 0, 0 to check. So substituting that in my original inequality, 4 times 0 plus 4 times 0 is less than 2. 0 plus 0 less than 2, or 0 less than 2 is true. Okay, now finally we have a system here. On this same set of axes, we're going to graph two inequalities. Now there's not as much work to do because they're both in slope-intercept form. So let's say we're going to do this one first in blue. The blue one has a slope of 1 and a y-intercept of 2. So did that backwards. The y-intercept is 2, the slope is 1. So rise 1, run 1. Rise 1, run 1. Rise 1, run 1. Until you feel like you can graph an accurate line. This line will be dashed because it's just greater than. And again, it's already in slope-intercept form, so we can trust this sign. The greater than tells me to shade everything above this line. Okay, we'll do this other line in pink to differentiate it. This one has also a slope of 1, but now a y-intercept of 5. So y-intercept 2, 3, 4, 5. Slope of 1 again. So 1, 1, 1, 1. Also a dotted line. Did I get crooked there? Okay. And this one shades below that line. So we will shade everything under the pink line. Now, the spot where I overlapped, where I shaded both pink and blue, is between the two lines. So I might darken that with a purple shade here. This would actually be all of the points, there are infinitely many of them, but all the points that satisfy both inequalities, so the solution to that system. So what value do these two inequalities have in common? Now, I had to read that question a couple times to really understand what they were asking me for, but it's referring back to the actual inequalities. What was the same about both of them when they were in slope-intercept form? And they had the same slope, which was 1. Now, how is that significant? That's the reason that the two lines ended up parallel, and we were just shading between those two parallel lines.